Hi, I'm going to explain a research paper titled Human Voice Sentiment Identification published at ICTCS 2020 as a part of my short story assignment for my course CMP 255 Data Mining. Little about the topic. Introduction about the topic is sentiment plays a vital role in human beings and it is used to find the mindset of the human beings and also known as speech emotion recognition. And their development in these fields from various companies like various products like Amazon Alexa, Google Home, Apple HomePod. The main purpose of sentiment identification is the enhancement of man-machine communication. And the steps followed in the research paper are data collection, data pre-processing, feature extraction, dimensionality reduction, training and testing model, and the results. The data set used in the data set used in the research paper is Berlin Speech Database, which is from University of Berlin, and the language in the audio signals is German. There are 10, and the audios is consists of 10 actor voices, 5 female and 5 male. Signals are recorded at the sampling frequency of 48 kilohertz and downsampled to 16 kilohertz. There are total of 311 samples, and the sentiments in these audio samples are fear, anger, happiness, sadness, and these and there are 70 samples of sad sad, and 66 samples of happy, and 65 fear, and 110 of anger. As a next process in the paper, it's a pre-processing. So we have to do a pre-processing of the audio signals because when people communicate, it includes pause, up and down, high and low pitches, and a lot of fluctuation. So to handle this, we remove the silent portions and noise portion of the signal. And as the next step of the pre-processing, there is framing. In this process, we divide the signal samples which are gained by the analog to digital converter, and these small samples are called frames. A signal is divided into n samples separated by a duration of 10 milliseconds, and each frame is of 20 to 40 milliseconds. And the next step, we do windowing. It is used to minimize the spectral distortion of the window to reduce the thickness towards on the ends. The signal is padded with zeros at the start and end, and the start and end of the signal. And in the research paper, Hamming window technique is used on the frames. Why do we do windowing? Windowing is done because a computer cannot deal with infinite number of data points. So all the signals are cut off at the ends, and this causes the ripples on the either end of the peak. And the technique used, Hamming window, will reduce the ripple, given uh, a more accurate idea of the original frequency spectrum. And in the next step, and these three steps include in the pre-processing. And in the next step, we do Fourier transform. And Fourier transform is applied to convert the voice signal from the time domain to frequency domain. This is to identify the frequencies in each frame. And in the next step, MEL filter bank and the frequency wrapping is used. MEL filter banks will give a better resolution at low frequencies and thus at high. And the triangular filter banks are used, and these help to capture the energy at each critical frequency band and roughly approximate the spectral range. And in this step, the MEL frequency spacing is below 1000 hertz, and in between 20 to 40 triangular filters. The most standard number of triangular filters used is 26 with 50% overlapping. And 26 triangular filters are used in the research paper also. And these frequencies are converted on a MEL scale using a log formula. And this scale will tell us how to space the filter bank and how wide we create them. Once we get the values on the MEL scale using the log formula, then we apply a discrete cosine transform. We convert these log MEL frequencies to a time domain to get the MFCC coefficients, which is MEL frequency substrate coefficients. And once the pre-processing is done, features are extracted from the audio signal. The main features are pitch, bandwidth, energy, frequency, and MFCC, MEL frequency substrate coefficients. Um, pitch is the number of variations per second. Pitch estimation is designed to estimate the pitch or the fundamental frequency of the oscillating signal. And formant frequencies are used, especially the resonance frequency of the vocal track. And these frequencies are calculated using a linear predictive coding. And it is a method used mostly in the audio signal processing and speech processing for representing the spectral envelope of a digital signal. And a linear predictive model is used in linear predictive coding. And this is a mathematical operation where future values of a discrete time signal are estimated as a linear function of the previous samples. And the next feature is MFCC, MEL frequency substrate coefficient, which is the coefficient that constitutes the audio based on the perception. It is derived from the Fourier transform of the discrete cosine transform of the audio group. Once all the features are extracted, the next step is to reduce the dimensionality of the data set. And principal component analysis technique is used to reduce the dimensionality of the data set. Here, the input for the PCA will be n cross m feature matrix X, and the output will be n cross k feature matrix, where k is less than m. And the steps in the principal component analysis are, as a first step, we take the feature vector matrix data collected from the feature extraction method. And the next step, we subtract the mean value from the data dimension. Subtract the mean value from the data to normalize it. In the next step, we compute the covariance matrix of the normalized matrix. And the next step, once the covariance matrix is computed, we find the eigenvectors and eigenvalues of the covariance matrix. And we choose the next step, we choose the we choose the eigenvectors which has the highest eigenvalues, and number of eigenvectors depend on the variance they cover of the data set. And the new matrix is derived from the feature vector matrix and the original data. Once the dimensionality reduction technique is applied on the data set to avoid the curse of dimensionality, and to predict the classes of the data set, we use support vector machine to divide the data set into classes, and multi-class SVM classifier is used as data set is divided into 4 different classes. And little about the support vector machine. SVM are more commonly used in the classification problem, and SVM are based on the idea of finding a hyperplane that best divides a data set into 2 classes, as shown in the figure. This is a representation of a binary classifier where this line is an hyperplane which divides the data into 2 classes, saying these data sets are classified into an C1, and these other 2 data sets are classified into C2. And the right hyperplane is the one best segregates the 2 classes within the data. And the distance between the hyperplane and nearest data point from either set is known as the margin. The goal is to choose a hyperplane with the greatest possible margin, so that there are a greater chance of new data being classified correctly. So there is And coming to the results in the research paper is the overall accuracy of the model is 84.99. So this is a little about the new research paper which I have explored. I have explored, and I have uh, built a collab to work with the to use some of the concepts which I explored in the research paper. As a first step, I have imported all the libraries which are useful for building the model, and I have loaded the data from the drive. And and little about the data set which I used. I have used a Radis data set which contains 1,440 files. Which has 24 professional actors, 2 female and 2 male. I have used this Radis dataset because it is the audio signals, the language in the audio signals is in English, and it has more samples than compared to the dataset used in the research paper. And the speech emotion include calm, sad, happy, angry, fear, surprise, and disgust. The file names has a seven part numeric unique identifier. The identifier consists of similar characteristics. The first part defines if the file is an AV, full AV, or video only or audio only. And the second part defines if it is an either a speech, either an either a speech or a song. And the third part defines the emotion, which is the target label of the file. And fourth defines the emotion intensity. It is either normal or strong. The data set has two types of statements. Kids are talking by the door, and dogs are sitting by the door. And the sixth part says the repetition is the audio is in first repetition, the second repetition, seventh one is a unique identifier of the actor's voice, representing the actor's voice. And once the data set is loaded, as a first step, we are getting the target labels for the audio files from the file names. As it is mentioned in the data set, the third part of the file name is the emotion label, and that is extracted and stored in an emotion label. And emotion label is an integer value, and which is converted into a string value using the dictionary. And the data set is stored in this way. The emotions is the target label, and the path of the audio file is stored in the table. Once the data is stored and the label and the target label is extracted, we have I have explored the data. As a first step, I have count of each emotions in the audio files. As we can see from the bar diagram that all the emotions, the count of all the emotions is same except for the neutral. And to explore more about the data, I have plotted the wave plot and spectrogram on the audio signals. Wave plot is used to get the pitch of the audio signal with respect to time, and spectrogram is used to get the power spectrum movement of the audio signal. And little about the spectrogram of audio signal, which a spectrogram is a visual way of representing the signal strength or loudness of a signal. Over time, at various frequencies, spectrogram tells about the quality of sound. And this is seen with different colors at different levels at a particular time. Black to red, which is a low volume, and yellow to white is a high volume. For the first data set, it's happy audio. For the happy audio signals, we can we have plotted the spectrogram and wave for the happy audio signal. And for the happy audio signal, we can conclude from the spectrogram that the volume of the audio is very low, or you can say the volume is not present for the at the start and end of the voice signals, and the volume is clear and loud at the middle of the signal. As we can see here, it's clear and loud, as yellow color is seen in the spectrogram. And in the same way, for the angry signal, the audio is too loud, and the audio signal's clarity decreases for the at a particular time with the frequency. And for the sad signal, the volume of the signal is low and clarity decreases as at a particular time with the frequency. And for the fear, the audio signal is low and the statement has the clarity at the lower frequency at a particular time. That it decreases as frequency at a particular time. And once the data is explored, I have used data augmentations, pitch, stretch, shift, and noise. What are data augmentations? Data augmentations are the techniques used to modify the data and a new synthetic data. This acts as a regular equalizer and reduce the model from overfitting. So I have used noise disturbance is added to the audio signal, and the other is stretch of the audio signal by a fixed rate, and the shift is an shift in the audio signal by a random sequence, and the pitch is changed randomly. And I have applied these augmentations on the signal to see how actually the audio signals comes out when a noise is added. And I have used the Librosa library to perform all these operations, all these techniques on the this is I have applied a noise on an audio signal. So this is a fear audio signal where a noise is added to it. And in the same way, a stretch is added to the audio signal. So we can see that the duration of the audio signal is increased by a stretch, and in the same way, shift and pitch is also added. Once, once we once as a next step, I have done a feature extraction with data augmentation added to the data set. So the features are chroma shift, and that the chroma value of the audio basically represents the intensity of the audio signal, and MFCC is used in speech recognition system and is also used in finding the audio similarity measures. In feature extraction, the features are chroma, MFCC, and these values are calculated using the library Librosa on the audio signals. And as I have said, I have applied the data augmentation, stretching, and pitching on the data set on the audio signals, and these are added synthetic data to the data set. And the target label, out of all the emotions in the audio signal, I have considered the angry, happy, sad, and fear as in my target labels. And I have taken the audio signals which has the angry, happy, and sad and fear. Once the features are extracted, we get a features of 161 columns. As it's very high, it can lead to the cause of dimensionality, as there are many dimensions. So I have used the dimensionality reduction technique PCA to reduce the features to 40. Once PCA is applied, once and dimensionality of the data set is decreased, that data set is decreased. I have split the data set into training and testing data set. Once the training and testing data set has split, then we built a model. I have used the support vector machine for the multi-class support vector machine to build a model on training and to predict the values for the testing data set. I have used linear and polynomial kernels of the support vector machine. And for the accuracy for the polynomial kernel, support vector machine is 40%, and for the linear kernel SVM is 61%. It's 61%. So, and this is a confusion matrix for the linear kernel SVM, which includes happy, sad, fear, and angry, happy, sad, and fear. As in the above step, I have extracted the features by adding the data augmentations to the data set. And here I have applied as data augmentations highlighted so that the model is a model is not overfit on the data, not doesn't lead to overfitting. So I have applied the I have also checked to the accuracy of the data set without adding the data augmentations. The features extracted are the same, the chroma shift and MFCCA and MEL using the Librosa library. Once the features are extracted and the data and the feature and the data set is split into uh, training and testing, I have applied the damage reduction technique PCA to reduce the number of features into 40. And I have applied the same support vector machine model on the training data to fit the training data set and to predict the values for the testing data set. And for the accuracy of for the with the polynomial kernel is 44%, which has increased a little bit, and the accuracy compared to the feature extraction with data augmentation, and accuracy of the model with linear kernel is 61%, which is same as before. I have also used the MLP classifier. This classifier has a neural network built in it, and I have used this classifier to fit the training and predict the values for the test data set. And the accuracy for this data set with the model MLP classifier is 81%, and the confusion matrix is, and this is the confusion matrix. So I have built this collab using the techniques learned in the research paper and also from the references of the research paper and some of the techniques which I have found in the internet to handle the audio signals. And learning the concepts from the research paper and building the collab to identify the sentiment of the audio signal gave me an overall idea of how to work with the audio signals. And I have learned the pre-processing techniques and important features to be extracted from the audio and data set, mostly the important features to be used in the data mining, in the techniques when applied to the audio signals. And I have also learned how to build a model when which is not which is not overfit. And the model I built using the concept learned from the research paper, using the on the radius data set, using the 61% accuracy using the support vector machine and support vector machine model, and 81% using the MLP classifier. As the next step, I'll be working on the more techniques to increase the, as this is my first time handling the audio signals. I want to extend this to learn more about more techniques to increase the model accuracy and learn methods to handle audio signals data. Thank you and good day.